Did you know that every carbon atom in your heart, every oxygen atom you breathe, was once forged in the heart of a dying star? We don't just live in the universe, we are a part of it. The elements that make up your body weren't born on Earth. They were created in the nuclear furnaces of the first stars over 13 billion years ago and scattered across space by powerful supernova explosions. Our universe, once an unimaginably small singularity, hotter than millions of suns combined, exploded in the event we call the Big Bang. Since then, for 13.8 billion years, it has been expanding, giving birth to everything from the cosmic microwave background to massive galaxies, from the first light of population 3 stars to our own solar system and Earth. So how did the universe come to be? Why is its expansion accelerating? Will it come to an end? And what happens after the heat death of the universe? Today, join me, a passionate explorer of the cosmos and space science, as we travel back in time to uncover the very first moment, 10 to the minus 43 seconds after the Big Bang, when space, time, and matter didn't yet exist. The dawn of the first stars, when the universe lit up for the first time. The formation of Earth, water, and primitive life from deep-sea hydrothermal vents. And finally, a distant glimpse into the dark future of galaxies, black holes, and the ultimate fate of everything, the slow fade into cosmic silence. Together, we'll unravel some of the greatest mysteries modern science has yet to solve, from dark matter, dark energy, to the elusive theory of everything, the dream pursued by physicists like Einstein, Hawking, and Penrose. If you love the universe, don't forget to like, subscribe, and turn on notifications, so that every new video becomes a new step with me into the deep history and grand destiny of us all, the thinking Stardust. The origin of the universe, the Big Bang, 13.8 billion years ago, before there were twinkling stars, before the Earth orbited the Sun, even before the very concepts of space and time existed, our universe is believed to have begun from a single point, infinitely small, infinitely dense, and unimaginably hot. That point didn't explode into a fireball. Instead, space itself began expanding, suddenly and entirely. This phenomenon is what we now call the Big Bang. There are no boundaries in time, just as there are no edges in space. The universe is a closed system with no beginning or end. Stephen Hawking, A Brief History of Time. 100 million trillion trillionths of a second after the Big Bang, the Planck era. The first moment that modern physics can even attempt to describe occurred about 1/10,000 quadrillionth of a second, written as 10 to the minus 43 seconds, after the birth of the universe. This is known as the Planck era. At that time, the temperature of the universe was a staggering 10 million trillion degrees Kelvin, around 10 to the 32 Kelvin. At such temperatures, all known physical laws break down. There were no atoms, no light, only a primordial sea of pure energy. At this stage, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are thought to have been unified into one single superforce. But after just a brief instant, gravity was the first force to separate, setting the stage for the universe's complexity and evolution. 1 million trillion trillionths of a second after cosmic inflation. Immediately after the Planck era, the universe entered a period of rapid expansion. In less than 1 million trillion trillionths of a second, the universe expanded by a factor of over 100 million trillion times, from smaller than an atom to about the size of a soccer ball. This event is known as cosmic inflation. Inflation doesn't just explain the large-scale structure of the universe. It's the miracle that makes everything oddly understandable. Alan Guth, father of the inflation theory. Inflation solves a key mystery. Why does the universe look nearly the same in every direction, even though distant regions could never have communicated with each other at the speed of light? 1/10 billionth of a second after the birth of fundamental particles. As the universe cooled to around 10 trillion degrees Kelvin, pure energy began transforming into matter. Quarks bonded together to form protons and neutrons, the basic building blocks of atomic nuclei. The weak nuclear force, responsible for radioactive decay, became distinct and contributed to a slight imbalance between matter and antimatter, a crucial reason why matter survived in today's universe. around 3 minutes after the Big Bang formation of atomic nuclei. When the universe cooled further to about 1 billion degrees Kelvin, protons and neutrons began to combine into the first atomic nuclei. This process is called Big Bang nucleosynthesis. As a result, about 75% of the universe's mass became hydrogen-1, superscript 1H. Roughly 24% turned into helium-4, He. A trace amount became deuterium, superscript 2H, helium-3, and lithium-7. What's remarkable is that some of the oldest stars, known as population 2 stars, still carry chemical signatures that closely match the predicted element ratios from Big Bang nucleosynthesis. This is one of the 3 strongest pieces of evidence supporting the Big Bang theory, along with cosmic background radiation and the expansion of space. The Dark Ages, the sleeping universe phase, from 380,000 to around 200 million years after the Big Bang. After the first light, the lights went out and darkness ruled. About 380,000 years after the Big Bang, the universe had cooled down to around 3,000 Kelvin, roughly 2,727 degrees Celsius. At this temperature, free electrons began to combine with protons to form neutral hydrogen atoms, a process called recombination. Photons, which had previously been scattered constantly by free electrons, were now released and could travel freely through space. This release of light formed the cosmic microwave background, CMB, a faint glow that we can still observe today. However, after this first light, the universe entered a time of complete darkness. No stars, no galaxies, nothing to shine. The universe's composition, a sea of primordial gas. At this stage, the universe consisted mainly of hydrogen, making up about 75% of the total mass, helium about 24%, traces of lithium, deuterium, hydrogen-2, and helium-3. These elements had formed earlier during Big Bang nucleosynthesis and now floated through space, extremely cold and thin. There were no heavy elements like carbon, oxygen, or iron, since those would only form later inside stars and during stellar explosions. The universe was almost entirely uniform except for tiny ripples in matter density, the early fluctuations we still see today imprinted in the CMB. Cold as the heart of space. Because the universe continued to expand, its temperature kept falling, from about 3,000 Kelvin to around 100 Kelvin after several million years. And by the end of the Dark Ages, down to roughly 60 Kelvin, which is minus 213 degrees Celsius. This was not enough heat to produce light, not enough gravity to form stars. The universe was essentially in a deep cosmic sleep for hundreds of millions of years. Why call it the Dark Ages? Astronomers refer to this era as the Dark Ages not only because there was no visible light, but also because there were no electromagnetic signals other than the CMB. With no stars, there were no visible or ultraviolet light, no ionization of gas due to the lack of energetic photons, no tools for traditional telescopes to observe this period. It truly is a blank space on the timeline of the universe, invisible but vital. What was happening in the darkness? Even though we couldn't see it, crucial events were silently taking place. Gravity began to act. Slightly denser regions, caused by early matter fluctuations, began to pull in more gas. Clouds of primordial hydrogen, though extremely thin, started to clump together under gravity. Some theories suggest that dark matter acted as a cosmic scaffolding, helping these gas clouds stay bound. But this process took hundreds of millions of years, as matter was sparse, gravity was weak, and space was still expanding rapidly. Why is this period so important? The Dark Ages laid the foundation for all cosmic structures that would follow. Galaxies, galaxy clusters, superclusters, the cosmic web. Everything began here, from the tiny ripples in early matter density. The role of the James Webb Space Telescope, JWST, launched in 2021. The James Webb Space Telescope is our first real window into the universe's deep past, peering closer than ever to the end of the Dark Ages. Can detect the faintest infrared light from the first stars and galaxies, whose light has been stretched and redshifted over billions of years. Spot the first tiny glimmers of light, the moment the darkness ended and the epoch of reionization began. If the first light was the universe's dawn, then JWST is a time-traveling telescope, letting us witness that moment from the future. Avi Loeb, astrophysicist, Harvard University. The dawn of stars, population 3, from 200 to 500 million years after the Big Bang. After hundreds of millions of years shrouded in darkness, the universe finally began to light up. The first light did not come from the sun or any galaxies, but from the very first generation of stars, a kind never seen before. Astronomers call them population 3 stars, often described as the cosmic torches that lit up the early universe. What makes population 3 stars so unique is that they were formed entirely from hydrogen and helium, the only two elements that existed at the time, created just minutes after the Big Bang during primordial nucleosynthesis. These stars contained no heavier elements like carbon, oxygen, or iron, what astronomers collectively refer to as metals, because there were no metals to help cool the gas clouds. These primordial clouds had to collapse into much larger masses before they could ignite and form stars. As a result, population 3 stars were enormous, with masses estimated to be 100 to 1,000 times the mass of our Sun, far beyond the size of most stars we see today. However, their colossal size came with a cost, very short lifespans. A population 3 star likely lived for only 2 to 3 million years before ending in a powerful supernova explosion. Compared to our Sun, which has a lifespan of about 10 billion years, these stars lived and died in what amounts to a cosmic blink of an eye. Yet, when they exploded, they did more than just vanish. They sowed the seeds of life. Inside their cores, hydrogen atoms were fused into helium, and through even more intense reactions near the end of their lives, heavier elements such as carbon, oxygen, nitrogen, silicon, and iron were formed. These elements were then blasted into space when the stars exploded, becoming the first raw materials for building the next generations of stars, planets, and eventually life itself. Without these explosions, there would be no Earth, no water, no trees, and no humans. Another vital role of population 3 stars was their emission of intense ultraviolet UV radiation. This high-energy light had enough power to break apart neutral hydrogen atoms floating through the universe, separating electrons from protons, a process known as the epoch of reionization. Before this, after the universe cooled and the cosmic microwave background, CMB, was released, space had once again become murky due to neutral hydrogen-absorbing light. But the UV light from these first stars changed that. It reionized the universe, making it transparent once again, allowing light to travel freely and marking the beginning of an era where we could observe galaxies, star clusters, and eventually planets like Earth. To this day, we have never directly observed a population 3 star. They lived too early and died too far away. What remains are chemical fingerprints found in later generation stars, and perhaps the faint echoes of ancient supernovae, which telescopes like the James Webb Space Telescope, JWST, are now trying to detect. Even though we've never seen one, scientists strongly believe population 3 stars were the first link in the chain that led to everything we know. The elements that make up water, the structure of galaxies, and even the atoms that form you right now. They were the first artists in the cosmic workshop, forging and breathing life into a new world hidden in darkness. Without them, there would be no us. So if you've ever asked, where did we come from? This is your first real answer. From the ashes of nameless stars at the dawn of the universe. The birth of galaxies, from 1 to 3 billion years after the Big Bang. After the first stars were born and blew their material into space through powerful supernova explosions, the universe was no longer a still and lonely place. Now, under the quiet yet persistent pull of gravity, an organized cosmos began to take shape. Galaxies, the cities of stars, began forming in the darkness of the early universe. In regions where matter was just slightly denser, Even by only 1 part in a million, gravity began pulling hydrogen gas, helium, and cosmic dust together. Over hundreds of millions of years, these immense gas clouds collapsed and clumped together, giving rise to the first galaxies, enormous structures containing millions or even billions of stars. GNZ11, a light fossil of the early universe. One of the oldest galaxies ever observed by humanity is called GNZ11. It looks nothing like familiar galaxies such as our Milky Way. It is much smaller and extremely young. GNZ11 was formed only about 400 million years after the Big Bang, when the universe was just around 3% of its current age. What's truly remarkable is that light from GNZ11 took over 13.4 billion years to reach Earth, because it lies an astonishing 13.4 billion light-years away. In other words, when we look at GNZ11 through a telescope, we are seeing it as it was in the infancy of the universe. Observing a galaxy this distant is like finding a baby photo of the cosmos. It allows astronomers to test theories about how cosmic structures formed, how, in just a few hundred million years, chaotic clouds of gas and dust assembled into the first star clusters and galaxies. From primitive galaxies to grand cosmic structures. Early galaxies like GNZ11 often had unstable shapes, not the smooth spiral forms we're used to today. They appeared as tiny, irregular patches of light, forming stars at a much faster rate, sometimes dozens of times faster than the Milky Way does now. Over the course of billions of years, these galaxies collided, merged, and grew. Some of the larger galaxies developed dense central cores, where supermassive black holes began to form, playing a crucial role in the later evolution of galaxies. Our own Milky Way galaxy, home to Earth, is thought to have begun forming around 1 to 2 billion years after the Big Bang, although it took several more billion years to settle into its current spiral shape. Did you know? A galaxy like the Milky Way contains between 100 and 400 billion stars. The observable universe contains more than 2 trillion galaxies, a number beyond imagination. Galaxies are separated by millions of light-years, yet still interact through gravity, creating spectacular cosmic collisions that can last for billions of years. Looking into the past with telescopes, observing ancient galaxies like GNZ11 is not like looking at a photo. Their light has been stretched due to the expansion of the universe. This phenomenon is known as redshift. GNZ11 has a redshift of about Z is almost equal to 11, meaning its light has been stretched 12 times longer than when it was first emitted. Only modern space telescopes like the James Webb Space Telescope, JWST, are sensitive enough to detect the faint infrared light from such distant, ancient objects. Each galaxy is like an ancient journal, telling the story of the universe's journey from darkness to light. The emergence of galaxies shaped the entire structure of the cosmos as we know it. And within the flow of their light, something truly miraculous began. The rise of planets, life, and eventually humanity. The solar system and Earth, approximately 4.6 billion years ago. Billions of years after the Big Bang gave birth to the universe, the first stars had already lived, died, and exploded in violent supernovae. Their remnants, heavy elements like carbon, oxygen, iron, and silicon, drifted through the cold, vast emptiness of space, mixing into interstellar gas clouds. One of these clouds, around 4.6 billion years ago, began to change. That moment marked the beginning of a story that would eventually lead to the formation of Earth, and to us, the collapse of the solar nebula, a massive molecular cloud, what we now call the solar nebula, full of cosmic dust and cold hydrogen and helium gas, began to collapse under its own gravity. It may have been triggered by a nearby supernova explosion. As the cloud collapsed, it started to spin faster, just like a figure skater spins faster by pulling in their arms, flattening into a protoplanetary disk. At the center of that disk, most of the mass, about 99.86% of the total, collected into a massive object, the protosun, the birth of the sun. As matter in the central core was compressed, pressure and temperature rose dramatically. Once the temperature reached around 10 million degrees Kelvin, that is, 10 million times hotter than Celsius, nuclear fusion began. Hydrogen atoms fused into helium, releasing vast amounts of energy, the light and heat that we still receive today. That was the moment the sun ignited, becoming a young star shining in the vast universe. The formation of the planets. The remaining gas and dust in the disk, not enough to form another star, began to clump together to create planets, moons, asteroids, and comets. Depending on their distance from the sun and the surrounding temperature, different types of planets began to form. Closer to the sun, hotter. In the hotter inner regions, light elements like hydrogen and helium were blown away. Only heavier materials, metals, and rocks could remain. Result: formation of small, dense rocky planets like Mercury, Venus, Earth, Mars. Farther from the sun, colder. In the outer regions, cold gases could survive more easily. Large rocky cores in these areas were able to pull in huge amounts of gas from the nebula. Result: formation of giant gas planets, such as Jupiter, the largest planet in the solar system, Saturn, Uranus, Neptune. What is Earth made from? Earth, the third planet from the sun, was formed from the violent collisions and mergers of millions of rocky fragments called planetesimals. Over about 50 to 100 million years, these fragments smashed into each other at high speeds, heating the young Earth until its surface was covered in molten lava. Gradually, Earth began to cool. An atmosphere started to form, and water from comets may have brought the first oceans. We are, quite literally, made of star stuff. Every atom in your body, the carbon in your skin, the calcium in your bones, the iron in your blood, was once forged in the heart of a dying star. Carl Sagan. A quick timeline of key events. 4.6 billion years ago, a giant gas cloud collapses. The sun is formed. Between 4.5 and 4.0 billion years ago, the planets, including Earth, gradually take shape. Around 4.4 billion years ago, Earth cools and forms its first solid crust. Around 4.3 billion years ago, liquid water may have appeared, a first step toward life. Life on Earth. From stardust to the first organisms, the rise of life. About 4.6 billion years ago, Earth formed from the leftover dust and gas after the birth of the sun. But it wasn't until around 200 million years later, approximately 4.4 billion years ago, that the planet began to cool down after a period of intense bombardment by asteroids, meteors, and possibly even comets. It was during this chaotic era, known to scientists as the Hadean Eon, the primordial hell, that water may have first appeared. Some theories suggest that water was released from deep inside the Earth through volcanic eruptions. However, strong evidence also points to water-rich carbonaceous asteroids and ice-bearing comets crashing into Earth, playing a key role in creating the planet's first oceans. A few hundred million years later, as the surface cooled, the crust began to stabilize, and water pooled into oceans. Something extraordinary happened. Around 3.8 billion years ago, the first chemical traces of life began to appear in ancient rocks found in Greenland and Western Australia. These were not dinosaurs or anything we'd recognize. They were tiny primitive microbes living deep beneath the ocean, near hydrothermal vents. These organisms, called archaea, didn't need sunlight to survive. Instead, they drew energy from chemical reactions between minerals and the superheated gases rising from the Earth's interior. It was a dark world with no sunlight, but full of energy. Many astrobiologists believe that life could have started this way, not only on Earth, but also on ocean-covered moons like Europa or Enceladus. The oxygen revolution. The real turning point came around 2.5 billion years ago, when a new kind of bacteria emerged, cyanobacteria, also known as blue-green algae. Unlike earlier life forms that depended on chemical energy, cyanobacteria used sunlight to perform photosynthesis. They absorbed solar energy, split water molecules, and released oxygen gas, O2, the very air we breathe today. At first, this oxygen dissolved in the oceans and reacted with iron, forming layered iron-rich sediments called banded iron formations. But over time, the oceans could no longer absorb more oxygen, and it began to build up in the atmosphere. This event is known as the Great Oxidation Event, which took place between 2.4 and 2.1 billion years ago. Ironically, oxygen, which would eventually become essential for complex life, was toxic to many anaerobic organisms living at the time. Unable to adapt, many of these life forms went extinct. But from this mass die-off, a new opportunity emerged. With oxygen, cells could now produce energy much more efficiently. This breakthrough laid the foundation for the evolution of eukaryotic cells, multicellular organisms, and eventually the complex ecosystems we see today. If life is a grand symphony, the first notes were not played on land, not by humans, but by tiny invisible bacteria, quietly breathing and releasing a gas that would transform the entire planet. Oxygen wasn't something life needed at the beginning, but it was life that created oxygen, and in doing so, oxygen changed life forever. The future of the universe, from brilliant light to eternal darkness, a glimpse into the distant future of the cosmos. 5 billion years from now, the slow death of the sun. We are currently living in the vibrant midlife of the sun, the star that provides light, warmth, and life to Earth. But everything has a lifespan. About 5 billion years from now, the sun will run out of hydrogen fuel in its core. Without enough pressure from nuclear fusion to counteract gravity, the core will begin to shrink while the outer layers expand outward, turning the sun into a red giant, growing to hundreds of times its current size. During this phase, the sun may engulf Mercury and Venus, and possibly even Earth, turning our home planet into a glowing ember before completely destroying it. Eventually, the sun's outer layers will be blown away into space, forming a beautiful planetary nebula, while the remaining core collapses into a white dwarf, intensely hot, but no longer producing powerful light or energy as before. For billion years from now, a galactic collision. The Milky Way, the galaxy that contains our solar system, is not alone. About 2.5 million light-years away lies Andromeda, the nearest and largest neighboring galaxy. And the two are on a collision course, moving toward each other at over 400,000 kilometers per hour. In around 4 billion years, the Milky Way and Andromeda will collide. But don't imagine a fiery explosion. The distance between stars is so vast that most will pass by one another without direct collisions. However, gravity will twist and stretch the galaxy's shapes, eventually merging them into an entirely new galaxy, which astronomers have nicknamed Milkdromeda. By that time, the Sun, if it still exists as a white dwarf, will silently witness this grand cosmic reunion. 100 trillion years from now, the fading of starlight. Every star, including the Sun, is born, shines, and eventually dies. About 100 trillion years from now, the universe will run out of the gas needed to form new stars. This will mark the beginning of the degenerate era, a time when no new stars are born. The only remaining sources of light will be cooling white dwarfs, lonely neutron stars, and cold black holes. Light will fade. The universe will sink into eternal darkness. The death of everything, heat death. Once all the stars have gone dark, black holes will be the final cosmic objects left. But even they are not eternal. According to physicist Stephen Hawking, black holes will gradually evaporate over billions upon billions upon billions of years through a process called Hawking radiation. In this way, the universe will slowly lose all sources of energy. No more light, no more life, no more movement. As the universe's temperature approaches 0 Kelvin, absolute zero, where even molecules stop moving, it will reach its final state. Heat death, an endless, silent stillness that lasts forever. The journey to explore the universe has just begun. If you've enjoyed this incredible journey, from fundamental particles to stars, from the Big Bang to the edge of time, don't forget to like, subscribe, and share the channel so we can keep exploring even more wonders of the universe together. Got a cosmic mystery that makes you curious? Leave a comment below and I'll make a dedicated video just for it.